Hello, everybody. Today we are going to cover the ANOVA. This is your last inferential test for this course. There are a lot more, okay, but this is all you're going to learn. We're not going to talk about regression or anything else. So, what's special about it? It's definitely a little bit different than what you learned so far. It does have a couple of new concepts, I guess, that are differ a little bit than what you learned this far. So hopefully I will try my best to explain it to the best of my ability. Meanwhile, if anything is not clear, please feel free to email me, or when you see me on Friday, feel free to ask me any questions that you have. So the goals for today's lecture is to, first of all, be able to understand what an ANOVA is, okay, when do we use an ANOVA, how to calculate manually an ANOVA. We're going to actually use SPSS. I'm not going to open SPSS during this lecture. I'm just going to show you how to run it, but where I'm going to focus is how to actually interpret an ANOVA. And then we're also going to introduce a brand new concept that's called a post hoc test. And this is something that you haven't done this far. The good thing is that we're going to use SPSS to use it to do it, so you don't have to calculate it manually, but you do know how to interpret, because anytime you are having a significant ANOVA, you're going to have to run a post hoc, and this is where you actually going to be able to state your final conclusion. So this far, what have we learned, right? A z-test and a t-test, they both compared two groups essentially. Z-test was about comparing a population and a group, right? A sample rather, and then a t-test, it compared two groups on a dependent variable. Well, what do we do? We have more than two groups. Okay, apparently a t-test or a z-test won't cut it, so we need to have something else. So yes, we can actually compare the means of three or more groups, but we're going to have to use ANOVA. It's called the one-way analysis of variance, okay, or the F ratio of the F test. There's different names. It is the same thing essentially, and we use an ANOVA anytime that we want to compare, I guess, how different three or more groups are. So once again, a very important thing about running an ANOVA is, besides having three groups, your dependent variable that you're having, the one that you're actually comparing your three or more groups against it, it has to be measured at an interval or ratio level, meaning it has to be a real number. It cannot be a categorical variable, okay, such as, so you're going to be comparing, let's just say, three cities such as Anaheim, Fullerton, and Brea, and you want to find out maybe which one differs greatly in, height. Maybe people in Brea are taller than the people in Fullerton, and so on and so forth. So height, you can actually measure it, right, in inches or centimeters, depending what kind of measurement you're using. And you're going to be comparing three different cities, and you want to see if there's differences between that. GPA would be another thing that you can compare. So anything that you measure as a number, that's going to be your dependent variable, and your independent variable is going to be your groups, okay? So the best way, I guess, to understand an ANOVA is by going through an example. So here we have Dwight Schrute, okay, and he's an assistant to the regional manager for the Dunder Mifflin Paper Company. And I guess his boss asked him to figure out if there's significant differences in the amount of paper they sell between the three branches. So they have a branch in Scranton, Pennsylvania, one in Akron, Ohio, and one in Albany, New York. So Dwight is going to help us out, run an ANOVA, okay, and he's not going to run a t-test. And why would that be? Because a t-test compares the differences only between two groups, no more than that. You have to have only two groups. So now we're having actually three branches, so that means we cannot use a t-test. We are going to have to use an ANOVA. So what does it do, and how does it differ from a t-test? Remember the formula for the t-test, that it was x bar 1 minus x bar 2. So essentially you were subtracting the mean of the one group from the other one, and you were adjusting for any possible variance between the two groups. And apparently if their means were significantly different, then you would conclude that there are significant differences between the two groups. In ANOVA, though, we're going to do that, but it's a little bit different now because we're having more than two groups. So the thing is that there is a possibility that group one is different with group two, or group one can be different with group three, or group two can be very different from group three. So which one is it? Okay. So as you can see, there's different scenarios here. So the first thing that we need to test is if indeed we have any differences. But since we're having more than three groups, that means that there's a possibility that the group on itself might be very different. So the participants in group number one might be very different than, within themselves. Okay, and maybe in the other group, you might have a very homogeneous group, okay, that everybody has the same score essentially. So we need to worry about the differences between the different groups as well as the differences, the variances within its group itself. So essentially, ANOVA is a ratio, and as we're going to see, it's going to be a ratio for the variances between groups over the variances within groups. Okay? And guess what? What we want is a large ANOVA, a large F ratio. To understand that concept for the in between and within differences, I know a lot of students get confused with that concept. I'm going to give you a very over exaggerated example. Okay, so here we have in California, Minnesota, and Arkansas, and you, the researcher, you want to find out if there are significant differences between those three places. Do people in California watch more TV, or people in Minnesota or Arkansas? So you're interested to compare those three locations. So you go ahead, you go out there, and you interview six participants in every city. So the people in California, this is participant number one, number two, three, four, five, six, right? So they all said that on average they watch 10 hours of TV per week. Then you go to Minnesota, and every single participant tells you that they watch an average of 22 hours TV per week. You go to Arkansas and they're watching 31 hours of TV per week, but all of them watch the same amount of TV, which is of course a lot of TV. Probably it's too either too boring there or too dark or too cold, whatever it is, but they're definitely watching a lot of TV. But the idea here is what? That within the group of California, there's no differences, no variances. All the participants have the same score. Within the group of Minnesota, same thing. We do not see great variances within the group of Minnesota. But if you look across, you would say that the in between differences, in between meaning between California, between Minnesota, and between Arkansas, there's significant differences. Okay? So in this particular case, this is a very obvious example. In reality, you would never get six people rating the same thing exactly the same, but I just wanted to exaggerate here to really see the differences between having within the group differences and in between group differences. So now let's switch it a little bit. So let's just say that you go out there and you collect data on another six participants, but this time you get a little bit different answers. So your first participant in California tells you that they're watching 5 hours of TV a day. Then you interview another person in California, and he's telling you that they're watching 10 hours of TV per week, and so on and so forth. So here, what we notice on this table is that there's great differences within the group itself. So the participants from the California group, they differ greatly. Okay, as we can see, this person here watched 27 hours and this person watched only 5 hours, so there's large differences within the group. But if we look across, okay, we're going to see that now the differences between groups are non-existent because for whatever reason, again, this is not going to happen in reality, and that's why obviously we run the test, but the idea is that between the groups now we have no differences. All six participants between the six groups are very similar. Okay, in fact, in this particular case, they're the same. So in this case, we would say that we have no in between differences, but we have great within differences within our groups. Okay, and of course, that is what an F test is all about: is testing which one of the two is greater, and that will affect the overall F ratio that you're going to be calculating. So just like in the z-test and the t-test, we had a formula, okay? we are going to have a brand new formula for the F test, and it looks like that. Keep in mind, this is the short version. You're going to be using both, okay? So this is the F test or F ratio equal to the mean of squares in between over the mean squares within, okay? So the way I remember this, because a lot of students usually confuse which one goes because it's MSB, MSW, which one goes on top. I say to myself that B is comes before W, so B goes in the numerator, W goes on the denominator. Okay, so if I give you an word problem, the MSB and the MSW, then you can use this formula. But there's a possibility I might not give you MSB, okay, and MSW because this is not the full formula. MSB is actually equal to SSB divided by K minus 1. And what that is the sum of squares in between divided over K, which is the number of groups that you're having, minus 1. And your denominator is going to be equal to SSW, the sum of squares within, divided by your total n. And when I'm talking total n, I'm talking the total sum of all the participants in all groups. So if you're having, like in the previous case, you had 6 participants in each group and you had a total of 3 groups, that means you have 18 total. So your n would be 18, your k was 3, okay, so it would be right here 18 minus 3, that would be 15, okay. By the way, these guys here are your degrees of freedom. So k minus 1 is going to be your degrees of freedom for the numerator, and n minus k is going to be your degrees of freedom for the denominator. So F test, not that it's harder, it's just keep in mind that just like in every other inferential test, you're having degrees of freedom, which means you have to adjust, I guess, for any possible error. Now you're going to have to adjust for both the differences within and between, and that's why you're having degrees of freedom for both the numerator and the denominator. So when you're going to be using that F table that I'm going to show you later, you're going to be taking those two numbers into consideration as well, in addition to your alpha level. So essentially, this is your formula, okay? So the majority of your times, when I give you a word problem to solve using an ANOVA, most likely I'm going to give you the SSB, you're going to know the K, you're going to know the N, and then you can solve and find the F value. So why do you care about the F ratio? Why it's so important? And pretty much, how do you, I guess, understand it? What I want you to pay attention on this particular slide is the formula, and I want you to see that it is indeed a ratio between the mean of squares in between, which is essentially the variance within between the different groups, over the variances within the groups. In algebra, you know that when you have a fraction and your denominator is small, right, that means your F value here is going to be very large, which means it's going to be very close in value with the MSB, which means that whatever differences you find, you can attribute them in the differences between the groups. And that's what we want, okay? So we do want a large F value. But if the variance within the group itself are great, that means the overall fraction, okay, is going to be reduced. So your F value is going to be small. Most likely that means you're not going to be obtaining significant results, because in order to reject the null in an ANOVA test, you need a very large F value.